So today we are going to be graphing different transformations of functions, and what we really want to be focused on here is not necessarily making tables for each of these. We're going to know the pattern for the parent functions, and then we are going to use transformations in order to get these graphs more like really relatively close rough sketches. So I want to go ahead and list our parent functions, then we're going to talk about our transformations, and then we're going to go and do some practice, and we're going to wrap this up with a library of parent functions. So you know precisely how to graph each parent function, and then you can apply these different transformations. So the parent function for quadratics is y equals x squared. For absolute value, it's y equals the absolute value of x. For cubics, it's y equals x cubed. For square roots, it's y equals the square root of x. For rationals or reciprocals, this is y equals 1 over x. And then we have step functions, also called greatest integer functions. That is y equals the greatest integer of x. Notice that notation looks kind of similar to absolute value, but it's got brackets with like an extra line in there. We'll talk about that at the end, and we will practice and graph with that. Okay, so now a quick review of transformations. We have A, H, K, and B. You might not be as familiar with B. We'll talk about that one, and we'll practice some transformations with it. A is going to reflect over the x-axis if A is less than 0. So if A is a negative number, then you're going to reflect over the x-axis. A will vertically stretch our graph if the absolute value of A is bigger than 1. So if our A value is farther away from 0 than 1, then it's going to be a vertical stretch. So this includes numbers that are smaller than negative 1 or greater than positive 1. We're going to get a vertical compression when the absolute value of A is less than 1, or when A is between negative 1 and positive 1. If our A value is exactly 1, there will be no transformation that happens because of A. If it's exactly negative 1, it's going to reflect over the x-axis, but then you will not have any kind of stretch or compression. H is going to shift things left or right. It's going to shift it left if H is negative and right if H is positive, but please be careful. This is going to do the opposite of what it looks like in the equation. So when it's in the equation, I would see plus for left and minus for right, because remember, you have to take whatever's inside the parentheses with x, set it equal to 0, and then solve it for that h value. That's why we're going to see that sign switching there. K is going to shift things up or down, up if it's positive, down if it's negative. Okay, now our b value. B reflects things over the y-axis, and it is responsible for horizontal stretches and compressions. The way B is going to reflect over the y-axis is if B is less than 0, if B is a negative number. So that works very similarly to the way A works, it's just over a different axis. A horizontal stretch is when our B value is less than 1. So when B is in between negative 1 and positive 1, we're actually going to end up with a horizontal stretch. We will get a horizontal compression when our absolute value of B is greater than 1. So any numbers that are farther away from 0 than positive 1 or negative 1. So when B is less than negative 1 or greater than positive 1. And I want you to notice right now that this is the opposite from how A works. With A, stretches are numbers that are bigger than 1 or smaller than negative 1. Here, that's going to be a compression with our B value, a horizontal compression. With our A value, vertical compressions happen when A is in between negative 1 and positive 1. That will be a horizontal stretch. So it's opposite the way it works vertically. So when you see B in an equation, it is going to be inside the parentheses with x. So to figure out what's happening to our graph, you would take what's inside those parentheses, b of x, set it equal to whatever our output for our x value is. You're going to be dividing both sides by b. That is why when b is greater than 1 or less than -1, it actually results in a compression because we're dividing by that b value. And if b is a fraction, then you would multiply by the reciprocal. That's why it's going to result in a stretch. So if I have a fraction or a decimal out there, I'm going to multiply by the reciprocal, and that will stretch it horizontally. All right, we are going to practice graphing a couple quadratics using transformations. First, I want to graph the parent function so that I know the basic shape of all of these different quadratic graphs. So our parent function, we get to choose our inputs, we get to choose our x's. I always choose the same 5 whenever I have that option, -2, -1, 0, 1, and 2. And so we're going to take each of those x values and square it. -2 squared would give me 4, -1 squared is 1, then 0, 0, 1 squared is 1, and 2 squared is 4. So then I can get my parent function graphed here. Just like that. All right, so now that we have our parent graphed, we're going to graph our first transformation. I'm going to graph y equals -1/2 x squared. So this particular transformation has been reflected over the x-axis and vertically compressed by 1/2. So what this means, there's been no left or right shift at all, so all my x's are going to stay in the exact same spots, but all of my y's are going to be multiplied by -1/2. So I'm going to see them flip upside down, and I'm also going to see their distance away from the vertex cut in half. So that vertex isn't going to move, but when I move down from here, instead of being 1 unit away from the vertex as I move left and right, I'm only half a unit away from the vertex when I move left and right. For the next 2 points, those are 4 units higher than my vertex, so that's going to be cut in half. Now they're only going to be 2 units away from my vertex. And again, it's upside down because it's negative. And so I would trace in that graph. Notice it has been vertically compressed. It looks wider than the parent does. All right, scooting right along to our next transformation, I have y equals 2 times the quantity x minus 3 squared. That a value is going to vertically stretch my graph by a factor of 2. And h, remember it's the opposite of what I see there. I have to take those parentheses and set them equal to 0. So my h value is actually 3, which means we're going to be shifting to the right 3 units. So all of my x's are going to scoot to the right 3. That's going to take my vertex and move it right over here. All of my y values, my outputs, are now going to be 3 times the distance that they used to be away from the vertex. So again, instead of 1 unit up as I move to the left and the right, it's going to be 3 units away to the left and to the right. And the next one, instead of being 4 units vertically away from my vertex as I move left and right again, it's going to be 3 times more than that. So it's going to be 12 units away. My apologies, I just realized that I was using 3 there as my multiplier. It's vertically stretched by a factor of 2. So I misspoke there. So we're going to be a multiple of 2. Our distance is going to double. So I took off those 2 points there. So again, instead of being 1 unit away vertically as I move to the left and to the right 1 unit, it is now going to double that distance and be 2 units away to the left and to the right. As I continue moving left and right, instead of being 4 units away from my vertex, I'm going to double that distance. So now it is going to be 8 units away to the left and to the right. I apologize earlier for misspeaking. So I'm going to trace through those points and get my transformation. All right. We're going to do one more transformation of a quadratic, and then we will move on to the next function type. And I just can't seem to get this one correct. There we go. I got it that time. 3rd time's a charm, apparently. All right, last transformation of a quadratic. All right, so I have y equals 1/4 x squared plus 3. Notice that 1/4 is inside the parentheses with x. That means it's not my a value, it's It's not my h value because it's not being added or subtracted to the x. That is my b value. So the b value inside there, that fraction is actually going to stretch it horizontally by a factor of 4. And then it's going to shift my graph up 3. So it's been shifted up 3. That means my vertex is going to move right up here. I don't have a left or right shift, but we do have this horizontal stretch factor. So instead of moving to the left and the right 1, I'm going to move to the left and the right 4. Since I don't have an A value offering any kind of vertical stretch at the same time, I'm going to go out 4 units to the right and my vertical distance stays 1. Out 4 units to the left and my vertical distance still stays 1. Then I'm going to go out another 4 units and my vertical distance from my vertex is going to be 4 units. 1, 2, 3, 4. So right here. And then over here, 1, 2, 3, 4 more to the left. So that puts me over at -8. And then vertical distance from the vertex is 1, 2, 3, 4. So if you notice, this got very wide. That is why this is a horizontal stretch. I keep messing up the left-hand side of my parabolas here. A little bit wiggly, but you get the basic idea. All right, next we're going to move on to absolute value functions because those are very, very similar to parabolas. All right, absolute value function. So again, we get to pick our x's, and we're going to use that to find our y's. And on the parent function, we just want the absolute value of any of our inputs. So any negative inputs are going to have the exact same value, just positive. So -4 would result in a +4 output. -3 would result in a +3 output. -2 would go to +2. -1 would go to +1, 0, 0. And then 1, 1, 2, 2, 3, 3, 4, 4, and so on. So now I've got my absolute value parent function graphed, and we are going to do some transformations of the absolute value parent. So the first one we're going to do is the absolute value of 1/2, and then inside parentheses, inside the absolute value, I have x plus 3. So because that 1/2 is inside the absolute value and not outside of it, that makes it a b value. And since it's a fraction, that means we're going to have a horizontal stretch. Remember, if that was my a value, it would be a vertical compression. But because it's a b value in a fraction, this is going to be a horizontal stretch by a factor of 2. And then it's going to send me to the left 3. That's what that 3 inside of parentheses is going to do for it there. All right, so first thing I'm going to do is shift my vertex to the left 3. We're not going up or down at all, so it's going to be right there on the x-axis. And then this horizontal stretch by a factor of 2, that's going to take all of my x's and pull them out 2 units as I move up 1 away from my vertex. So these are going to be my points on my transformation here. And then I'm going to grab my straight edge and plot those, or connect those dots there. So there's my first absolute value transformation. All right, let's go look at our next absolute value transformation. All right, our next transformation is y equals the absolute value of x minus 5 minus 4. And this transformation, my h value is a positive 5, so this is going to send me to the right 5. And my k value is a negative 4, so this is going to send everything down 4. We don't have any stretches, any reflections, any compressions. So this is just going to translate each and every point, right 5 and down 4. So I'm going to move my vertex first. That would move my vertex to 5, negative 4. And then I know from there that I'm going to go up 1, right 1, and up 1, left 1 to get the remainder of this graph. And after I get all my points plotted, then I'm going to grab my straight edge and I'm going to finish out my graph. And there is my completed absolute value function that's been shifted right 5 and down 4. All right, let's do one more absolute value function, and then we'll move on to the next type of function. Okay, so this time we're going to graph y equals negative absolute value of 2x. So that negative out in front, that's our a value. That's going to reflect it over the x-axis, but the 2 inside the absolute value, that's a b value. That is going to horizontally affect it, and because it is a whole number, this is actually going to be a horizontal compression. So like I said, this is going to horizontally compress it. We're going to divide by 2, so it's going to cut that horizontal distance in half. So this is reflecting, so it's going to be upside down. We're not moving left or right at all. We're not moving up or down at all. So my vertex is going to stay put. Horizontally, I'm only going to go half the distance. Vertically, I will go the same distance, just down now because of that reflection over the x-axis. So at half a unit on either side, I'm going to be down 1 unit. And then I move another half unit to the right and to the left, and then a half unit to the right and to the left. But again, as I move these half units to the right and to the left, notice that my y values are still moving at 1 unit at a time. So vertically, I'm moving 1 unit away from my vertex, but horizontally, I'm only moving a half a unit away from my vertex each time. And then I'm going to trace through this. And there's my absolute value transformation. All right. Get ready for our next type of function. All right, so we're going to graph some cubic transformations now. Parent function is y equals x cubed. Similar to my quadratic functions, we're going to take each of our inputs, each of our x values, and we're going to cube them. So if I take -2 and I multiply it by itself 3 times, my output is -8. -1, if I cube it, my output stays -1. 0 cubed is 0. +1 cubed is 1. And +2 cubed is 8. And so here is my parent cubic function. All right, for our first transformation, we are going to graph y equals 1/2, then inside parentheses I have -x cubed plus 1. So this is going to be a vertical compression by 1/2. It's going to reflect it across the y-axis, and it's going to shift it up 1. So shifting up 1 is going to move my center point right here. We can treat it like our vertex. That's going to shift it up 1 since we're not going left or right at all. So that's going to move to right here. For my output, my y values, we're going to reflect them across the y-axis, and we're going to compress them. So it's going to be half the vertical distance. So before, this point right here was 1 unit away vertically from that center point. And so now it's only going to be half a unit away, but on the other side of the y-axis, so like this. And that's going to be true on the other side as well. The other 2 points, they were 8 units away from that center value. And so now that distance is going to be cut in half. So now they're only going to be 4 units away from that center point, and they are going to be on the other side of the y-axis. So even though it's only 4 units away, remember, because of that vertical shift of 1, that means that my topmost point that I'm going to graph now is at +5, and my bottommost point that I'm going to graph for this transformation is going to be at -3. But it still should be 4 units away from this center point right here. All right, so there's our first transformation of a cubic function. And we're going to do another one. Very basic transformation for us this time. Y equals x minus 4 cubed plus 2. That means my h is a +4, my k is a +2. That's going to shift my function right 4 and up 2. So every single point is going to translate right 4 and up 2. So my center point is going to come right here. right 4 and up 2, right 4 and up 2. So there's that side of my cubic like this. And then I'm going to do the other side, right 4 and up 2, and then right 4 and up 2. And then I can sketch in the other side of my cubic graph. All right, one more cubic transformation together, and then we're going to move on to square root functions. All right, so this time I have y equals negative, and then inside parentheses, 1/2 x cubed minus 1. So this is going to reflect it across the x-axis this time. This is going to be a horizontal stretch. Remember, if it's inside the parentheses with x, it's always going to be the opposite of what's expected. So this is horizontal stretch, and then it's going to go down 1. So the only thing that is going to affect that center point is the down 1 part. So down 1 will be like this. We're going to reflect across the x-axis. So the whole thing is going to flip over, and this is a horizontal stretch by a factor of 2. So each of my points horizontally is now going to double their distance from that center point. So remember, we've reflected it across the x-axis. So that means the 2 points on either side of my center point are going to look like this, a distance of 2 units away horizontally from that center point, and vertically 1 unit away. Then I go 2 more units away to the left and to the right, and I'm now going to be 8 units away vertically. So because of that downward shift of 1, that means I go up to a maximum height of 7 over here. That's not for my whole function, that's just where my point is going to be graphed. And then over here I go 2 more units to the right, and I need to be 8 units away from that center point. So this is my sketch of my cubic there. Notice that because a cubic function is an odd function, a reflection over the x-axis looks exactly the same as a reflection over the y-axis. All right, square root transformations up next. All right, parent function, y equals the square root of x. So I can't have any negative x values. The smallest one I can have is 0. And then I want other numbers that I can easily find the square root of. So the square root of 1 is 1. The square root of 4, that would be my input. Square root of 4 is 2, so that's my output. The square root of 9 is 3. And this is only going to point off to the right. It cannot extend to the left. All right, let's do some transformations of square root functions. First up, y equals negative 4 square root of x plus 2 minus 3. So we got a lot going on here. We have an a, we have an h, and we have a k. My a value is going to reflect it over the x-axis and vertically stretch it by a factor of 4. My h value is going to send it left 2, and k is going to send it down 3. The first thing I'm going to do as I graph this with transformations is I'm going to take the vertex, which is this farthest left-hand point here. I'm going to shift it left 2 and down 3 because any kind of reflections or stretches or compressions aren't going to affect my vertex at all, but left and right, up and down shifts will. So I'm going to go to the left 2 and down 3. So that's going to move right here. After that, my other points, now I care about that a value, that negative 4. So the negative is going to reflect it over the x-axis, and then it's going to multiply my vertical distance away from that vertex by 4. So instead of just being 1 unit away vertically, it is going to go 4 units away vertically. So there's my next point. And then I want to move from my vertex 4 units to the right, but now instead of being 2 units away vertically, I'm going to be 8 units away vertically, which actually takes me just off my graph here. So this is going to send it down like this. All right. Next transformation coming up. So we just had a reflection over the x-axis. This time my negative is underneath the square root with the x, so that's not going to be a reflection over the x-axis. That's going to be a reflection over the y-axis. And then that plus 3 on the end is going to shift it up 3. So again, I'm going to plot my vertex first. Going up 3 is going to move that up here. And then vertically, I'm going to be moving up 1 unit each time. And this time I'm going to be moving to the left away from my vertex to get that reflection across the y-axis. So instead of going up 1, right 1 to get my next point like the parent, I'm going to go up 1, left 1. From the vertex, up 2, right 4. So on my transformation, I'm going to go up 2 and left 4. And then this last point is going to be up 3 and to the left 9. So there would be my point there. With this kind of function, a square root function, this one is neither even nor odd. And so we do not have y-axis symmetry. We do not have y-axis symmetry and we don't have origin symmetry. So here a reflection over the y-axis looks very different than a reflection over the x-axis. All right, last one here that we are going to do for square roots, and then we have 2 more types of functions to talk about. All right, the last square root transformation that we're going to do is y equals the square root of 1/3, and then inside parentheses, x minus 1, and then plus 2. That 1/3, because it's underneath the square root, that is a b value. So that, remember, that's horizontal. And horizontal things always do the opposite of what it looks like in the equation. So that's going to be a horizontal stretch by a factor of 3. Then it's going to send my function to the right 1 and up 2. So my vertex needs to move first, right 1 and up 2. So right here. And then all of my other points are going to be stretched horizontally. So before I went up 1 and right 1, so now I'm going to go up 1 and right 3. For my next point from the vertex, to get the second plotted point on the parent, so I'm looking at this one right here, from my vertex back here, I went up 2 and to the right 4. So now I'm going to go up 2 and to the right 12. So up 2 and to the right 12, but I've already shifted to the right 1 because of that vertex shift. So that's going to send it out here to 13, which is quite a ways off my graph. So it's going to look like this. All right. Rational functions are our next to last type of function to look at. And rational functions get called reciprocal functions because when I go in to graph these, this parent, if my x is a fraction, my y is a whole number, and if my y is a whole number, then my x is a fraction. So if my if my x value is 1/2, my y value is up here at 2. If my x value is 2, my y value is at 1/2. Same thing with the 3's. It's going to be 1/3 on the x, 3 on the y, 3 on the x, 1/3 on the y. The only one where I hit a whole number point is 1, 1. So here's what I would see for this, but that's only checking my positive values for x. If I have negative values for x, so like a negative 1/2, that's going to be the reciprocal. My output would be negative 2. If I have negative 1/3, my output would be negative 3. If my input, my x, is negative 1, my output is negative 1. If my input is a a whole number, negative 2, then my y value would be negative 1/2. So right there. If my x is negative 3, then my output is negative 1/3. So we're actually going to have these asymptotes show up here on our rational functions. For the parent function, the asymptotes are the x-axis and the y-axis. All right, let's try a very basic transformation here. Y equals 2 over x. This 2 is my a value, and so that is going to vertically stretch it by a factor of 2. So I can use that A value to get a very simple rough sketch here. So now, when I have an X input of positive 2, my Y output is 1. When I have a Y output of 2, the X that gave me that was a positive 1. So notice I have points at positive 2 and positive 2 here. We didn't have any left or right shifts at all, so my asymptotes aren't going to change. And I should actually be getting closer to both axes here. So it's going to come around like this, and it's going to get real close to the x-axis there. And in this direction, it's going to get real close to the y-axis here. I'm going to see the same thing happen with the negatives. An input of negative 2 would give me an output of negative 1. An output of negative 2 means that I would have had an input of negative 1. So again, my asymptotes don't shift at all. I'm going to get really close to those axes, and then I can draw in my transformation. All right, let's try another transformation. This time we'll do some left and right shifting, which means our asymptotes are going to move here this time. All right, here's my next transformation. Negative 1 up on top, that's my A value. And so that means we're going to be reflected over the x-axis. Down here with x, this is the opposite of h. So my h is actually a negative 3 here. So I'm going to go to the left 3. And then our k value is negative 4, so we're going to go down 4. So the first thing I want to do is shift those asymptotes left 3 and down 4. Now my parent asymptotes are right on top of the x-axis and the y-axis. So down 4, that means my new horizontal asymptote is right down here. And then left 3 means my vertical asymptote has shifted right here. And then I can use that A value to plot, since we've reflected over the x-axis, instead of being in the first and third quadrants, I'm going to be in more like the new second and fourth quadrants. So I'm looking at where my asymptotes have shifted, and I know that I'm going to have a point right here on each of these. It's going to get real close to my asymptotes. Notice I am only 1 unit into each of those quadrants if I use my A value to get this sketch in here. So that's what my transformation would look like. When my A value is a positive 1 or a negative 1, I'm only really going to need 1 point plotted here to see what that's going to look like, and it's always going to be 1 unit into that quadrant. When my A value is more than 1 or less than 1, then I'm going to need 2 points plotted in each of the quadrants that's being divided up by my asymptotes. All right, let's do one more rational function transformation, and then we're going to look at our greatest integer function. All right, last rational function. So my A value is 4, so this is going to vertically stretch by 4. K value is 2, so we're going to go up 2. And then notice down in the denominator, my x is negative. That's technically where b goes, so this is a reflection over the y-axis. But because we're dealing with an odd function, that's going to look exactly like a reflection over the x-axis. So the only piece of this transformation that's going to affect my asymptotes at all, that's only affected by up, down, and left, right shifting. So up 2 is going to shift this asymptote up like this. But then my vertical asymptote is going to remain right on top of the y-axis like this. And then we have a reflection across the y-axis. So instead of being in quadrants 1 and 3, we're going to be in quadrants 2 and 4, but again, using those asymptotes as thinking about my quadrants now, because that has shifted. So it's going to be a vertical stretch of 4. So from where those asymptotes cross, I'm going to go up 1, 2, 3, 4, and I want to be into the correct quadrant 1 unit. 1, 2, 3, 4, and into the correct quadrant 1 unit. So in both directions, up and to the left, and then it's going to lay along this asymptote and it's going to curve through these points. This is what the stretch is going to do to it. And then in this other quadrant over here, from where those asymptotes cross, I'm going to count 4 to the right and 4 down. 1, 2, 3, 4. And I go into that quadrant 1 unit and then down 1, 2, 3, 4, and into that quadrant 1 unit. And then I'm going to sketch. It's going to hold tight against those asymptotes until I get near those points. It'll curve through those points and then it'll go and hug the asymptote again. So there is my last transformation for a rational function. One last type of function to look at here, that is our step function, our greatest integer function. All right, so with the greatest integer function, what we're looking for with this is we're going to move to the smallest whole number, the smallest whole integer. So basically we're going to take all of these and we are going to round down. So I want to practice with this first before we go and graph that parent function. So if I wanted the greatest integer, the biggest number that is close to 2.1 that is an integer, but I'm never, ever rounding up, the greatest integer that is achieved, you could think of it that way. So 2.1 would become the integer 2. 2.2, I'm going to round it down. That's going to become 2. Even 2.999, I go with the greatest integer. Well, it hasn't arrived all the way at 3 yet, so that's also going to be 2. 3.5, our greatest integer there is 3. I'm rounding down. 0.8, well, it hasn't gotten all the way to 1 yet, so our greatest integer there is 0. So really, when I'm looking at positive numbers, anything after the decimal point, I'm just going to completely ignore. It does not matter how big or small it is. With my greatest integer function, I am grabbing whatever that whole number is out in front for my positives. Now for my negatives, I'm going to round down. So if I'm at negative 3.1, that would be over here on the number line. I'm looking at the graph now. Negative 3.1 is going to be just to the left of negative 3. And so this is going to round down to negative 4. If it's helpful to look at a number line, then look at a number line there. This is going to go to negative 4. Negative 0.4, that would be about right here. This is going to round down to the greatest integer. So that's going to round down to negative 1. Negative 0.9 is also going to round down to negative 1. And negative 5.3 is going to round down to negative 6. So my greatest integer function, when I go to graph this, because everything is rounding down, this is going to end up looking like steps. I'm going to have a closed circle right here. And as I move over towards 1, the output is going to stay at 0, but I have an open circle there because it's anything smaller than 1 that's going to round down to 0. And then I would move up a step because if my input is actually the whole number 1, then my output would be 1. And that goes all the way up to until I'm almost at 2. So I have an open circle at 2, and all the values smaller than 2 but bigger than 1 are going to round down to 1. And I keep seeing this pattern repeat where it's a filled in circle on the left and an open circle on the right, and it looks like steps hanging out in space on my graph here. There we go. all the way up. So this is what the parent greatest integer function looks like. I can do that all the way up till I almost get to the corner over here. And then I can take it backwards as well. Open circle on the right, closed circle on the left, because everything is rounding down. Open circle on the right, closed on the left, until I get all the way to the bottom of this graph. We're going to do a couple transformations with this step function, and then we're going to look at a library of parent functions so that you have a handy reference page for all of the functions that we've been talking about and what their parent functions look like. All right, there's the end of our parent step function on this graph. All right, so doing transformations with my greatest integer function, I'm not going to graph the parent on here since we just graphed the parent. So let's start off with a very basic transformation. This one would have a vertical stretch by a factor of 3. Let me spell that correctly. Vertical stretch by a factor of 3. So my x's aren't going to change at all, but my y's, my outputs, mean that that vertical distance is going to be growing by 3. So this first step is still going to round down to 0. In between 0 and 1, everything's going to round down to 0. But then for the next step, if I have an input of exactly 1, well, now my output jumps up here to 3. And that's going to be my output all the way until I get over here, until I'm almost at 2. If I have an input of 2, then my output is going to jump up to 6. And that's going to be true all the way until I get over to an input value of almost 3. But if I have an input value of exactly 3, then my output jumps up here to 9. So these steps just became a lot steeper, a lot taller. And it's going to work the same way in reverse. Remember, I always want the open circle on the right and the closed circle on the left because it is rounding down. Oh, I put that one at the wrong spot. Here we go. There we are. All right. So there is a greatest integer function with a vertical stretch by a factor of 3. Let's try another transformation here. Okay, so now I have a greatest integer function of y equals the greatest integer of 1/5 x. Inside the greatest integer function means that that is not an a value, that is a b value, which means it's going to be doing the opposite of what an a value would do, and it's going to do it horizontally. So this is going to be a horizontal stretch by a factor of 5. All right, so now my steps are going to get longer, but they're not going to get farther apart vertically. So now from 0 all the way over until I'm almost touching 5. That's going to be one single step right there, all the way across. Filled in dot at 0 and open at 5. If my input is exactly 5, then I'm going to go up a step. So then I would have a filled in dot at 5, 1, and that's going to come all the way over, and then I would have an open circle at 10. I need to take my steps backwards as well, so open circle down here at -1, and that's going to extend all the way back to -5, closed circle on the left, and then I would take a step down, open circle there, and closed circle at -10. Remember, for any x value, I cannot have 2 closed circles at the same x value, because that would mean it's not a function anymore. That would mean 2 different outputs for the same input. So please make sure that one of your circles is filled in and the other circle is open. All right, let's do one last transformation of the greatest integer functions. All right, my last transformation here, y equals negative, greatest integer of x plus 2, and then plus 3. So this is going to be a reflection across the x-axis. So my steps are going to be going down. I'm going to move to the left 2 because of that h value, and I'm going to be moving up 3 because of that k value. All right, so what this is going to look like then, I'm still going to be rounding down, so I'm still going to have it filled in on the left and open on the right, but I'm moving to the left 2 and up 3. So here's where that first step would move to. And then this is going to walk down instead of walking up because of that reflection over the x-axis. So my next step would be down like this, and then I would have a step down here. And that's going to continue until I can't do any more on my graph. And I need to make sure that I also take it the opposite direction as well. But my greatest integer function, my step function, when it's been reflected, looks like it's walking down the stairs, or it's taking you down the stairs here. So there's all of that direction, and then I want to back this up also to finish out my greatest integer function here. Almost to the end of my graph. Oh, I did my circles backwards on that. Filled in on the left and open on the right. Greatest integer function always rounds down for us. All right, last thing I have for us now is we're going to go through a library of functions, which has transformation form as well as the parent function. And this is a printable sheet that you are welcome to print off of Canvas and then fill in to have as reference. All right, first up on our library of functions is a constant function. This is going to be a horizontal line, so the parent is f of x equals 1. So my parent function is a horizontal line that goes through 1 on the y-axis. Looks like this right here. This is going to have a domain of negative infinity to positive infinity, and it will have a range of whatever that value for b is. So for the parent, it's going to be 1. If that horizontal line moves up or down at all, then my range would be that new value. So this is just going to be a single value, just whatever our b is. Then we have linear functions, y equals mx plus b. The parent for that is f of x equals x. So that means my input and my output are identical. They're exactly the same. It's a perfectly horizontal line like this. My domain is all real numbers, negative infinity to positive infinity, and that is the same as my range, negative infinity to positive infinity. A square or a quadratic function. When I go to draw a quadratic function, the parent for that is f of x equals x squared. We practiced this in the video earlier. So my parent function has output values of 4, 1, 0, 1, and 4 for the corresponding x values of negative 2, negative 1, 0, 1, and 2, because we're taking each of those inputs and squaring them. My domain for all quadratic functions is all real numbers, negative infinity to positive infinity. My range depends on whether I'm concave up or concave down. If we are concave up, so if it opens up, then my range is going to start at my k value and go on to infinity. But if my function is concave down, then my parabola is going to open downwards, so it would be pointing to negative infinity, and it would reach its peak, its maximum, at k. All right, let's go look at the next 3 parent functions. We're going to do a cubic, a square root, and a cubed root next. All right, so for a cubic function, we're going to take our x's and we're going to cube them. So at -2, my output would actually be -8, which is off of this little tiny graph that I have here. And then -1, -1, 0, 0, 1, 1. We know it's going to curve through these points and then head down to -infinity. It's going to curve through these points and then head up to +infinity. So my domain is -infinity to +infinity. And my range is going to be the same. It is all real numbers. My ends are pointing in opposite directions. Right, square root functions. My parent, f of x, equals the square root of x. So I can only have positive x values, and I take the square roots of those in order to get my points. So 0, 0, 1, 1, 4, 2. My domain, if my graph has a positive b value, so underneath the radical with the x, in that case, my domain is going to go from h to infinity. It's going to point to the right, starting at wherever my vertex is. But if I have a negative b value, that's going to reflect it across the y-axis. And if that's the case, then it's going to point to the left, so -infinity, and it's going to go only as far as my h value to the right. My range, pretty similarly here, except I'm not looking at h because I'm not talking about left and right. For my range, I'd be looking at my k value. So if I have a positive a value, then the lowest this would ever go would be wherever k is, and then it's going to continue moving up there to infinity. But if we have a negative a value, if we've been reflected across the x-axis, then it's going to continue downward, and the highest point it ever achieves is our k value. All right, a cubic root function. So this is going to look almost exactly like my cubic function, except it's going to be flipped on its side, just the same way a square root function looks like half of a parabola flipped on its side. The difference between a cube root function and a square root function, though, is that with a square root function, I am not allowed to have negative values for x, or negative values underneath the radical. Cube roots don't have that same restriction on them. My cube roots, an input value of -8 is going to have an output of -2. An input value of -1 is going to have an output of -1, and then 0, 0, and 1, 1, and 8, 2. So it's going to look like my cubic function, but flipped on its side here. It continues to the left and the right forever, so my domain is -infinity to +infinity. And my range, this continues ever so slightly in the negative and positive directions vertically as well. So my range is once again all real numbers, -infinity to +infinity. So one of the things that I hope you're noticing as we talk about domain and range for these different functions, if it is an odd function, then my domain and range are all real numbers, -infinity to +infinity. But if I have an even function, then my range is going to be restricted. All right, let's do these last three functions: reciprocal or rational function, absolute value, and greatest integer. All right, last three functions here. So we're going to do our reciprocal or our rational parent function. We talked about this one when we were doing our notes. So we talked about how the input and the output will be reciprocals of each other, and it's going to hug along the x-axis and the y-axis without ever crossing them. And the parent will do that in the first and third quadrants there. So it's going to head along like this and then down like this. Domain for my parent function is going to go anything negative all the way until I get up to the y-axis, and then it picks up again on the other side of the y-axis, and it continues on forever to the right. So on my domain, it's going to be negative infinity all the way up to my h value. I have to leave my h value out, and then it's going to be a union picking up on the other side of my h value that gets left out, and it goes on to infinity. My range is going to do something very, very similar there because you notice I have an asymptote vertically there as well. So it continues down forever, it continues up forever, but it leaves out that horizontal asymptote. So this is going to go from negative infinity up to k, leave my k value out because there's an asymptote there, and then it's going to go from k to infinity. Let me make that just a little bit smaller so that I can fit it in the space that I've got here. There we go. Now it's not bleeding over into the absolute value function. Absolute value function, I've got my parent, f of x equals the absolute value of x. So on the positive side, my inputs and outputs are identical. And on the negative side, for negative 1, I'm going to get an output of positive 1. For an input of negative 2, I'm going to get an output of positive 2. So it's going to end up taking on this V shape here. And then I can use my straight edge to sketch my function in here. My domain on this, there is no x value that I cannot find the absolute value of as long as it is a real number. So this is going to be all real numbers from negative infinity to positive infinity. My range is going to be almost identical to what we talked about with quadratic functions. If this opens up, so if I have a positive a value, then my range, the lowest it ever goes is whatever k is, and it points up, so it goes up forever. If, however, I have a negative a value, if this opens down, then it's going to be negative infinity all the way up to my k value, and that would be the highest point. And then with my greatest integer function, the last parent function we need to talk about. Remember, this is my round down function. My parent is f of x equals the greatest integer of x. So it's going to round down to 0 for everything smaller than 1. It's going to round down to 1 for everything smaller than 2. It's going to round down to 2 for everything smaller than 3. Remember, closed dot on the left, open dot on the right. That's how it indicates that my output is always going to round down until I actually achieve that next whole integer. And that last step I put on there was wrong. All right, and then I need to make it go backwards as well. So on this function, any x value is going to have an output. I just did that one backwards as well. So my x's are going to be all real numbers, or negative infinity to positive infinity. But my range is only integers. It's only whole numbers. So this is all my integers. So integers we represent with like this fancy z. That's what we use to mean integers. Or you could write this inside curly brackets. So I would start with dot, 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 because it continues on forever in the negative direction. And then I can give some examples. So like -1, -2. I should switch those around because that's not decreasing order. So this should be -2 and then -1. And then 0, 1, 2, dot, dot, dot. This continues on in that pattern forever. All right, so that wraps up our discussion of graphing with parents and transformations. Tomorrow, we are going to be graphing something called piecewise functions. Please let me know if you guys have any questions. I am available
via Canvas messages or email, although Canvas messages are the best way to get a hold of me. Have a good one, everybody.